around the solar system than there is now. I mean, I think just a few days ago, there was an asteroid that came quite close to the Earth, and they say, gee, within the next 100 years, it might even collide with the Earth. And if it hits, it's going to cause some damage. Depends where it hits, of course. If it's Manhattan, it'll do significant damage. If it drops in somewhere in the Mojave Desert, it's going to knock out a few rattlesnakes. So, but this is an artist's depiction of what they think the early Earth was like. It's the only one I could get that was public domain. I don't know why they put the sun in the background like that, but anyways, it's referring to a time when we were being pelted so frequently by asteroids and comets that it was heating the surface of the Earth up to where the surface of the Earth was molten. Now, what's been driving this theory is that we really don't have evidence for rocks, permanent rocks, until about 3.85 billion years ago, 3.83, 3.82 billion years ago is the first time that you really see rocks existing on the face of the Earth in a permanent state. And the idea is, well, if the Earth was molten, you're not going to get rocks forming until that date. And this incidentally has implications for the origin of life, because we see origin of life on planet Earth occurring at the same time you get the first permanent rocks. Now before that you got some zircons, which show some evidence of carbonaceous molecules, but these are very hardy to temperature. Zircons can withstand way more heat than typical Earth rocks. Yeah, so the first time they actually get to see permanent rocks is the same date that you get the origin of life, which is a basis for the idea that the origin of life must have been a very rapid event, because as soon as you got temperatures that make life even possible, you got life right away. But the research paper that came out, and it was February 18th, so it's not too long ago, in Geophysical Research Letters, basically is saying we've had it wrong all these decades. The Hadean era was not an era when the Earth was hellishly hot. It was actually freezing cold. And so, yeah, the day hell froze over, it became kind of like this, where everywhere you look on the surface of the Earth, it's frozen. Now, we're talking roughly the first 700 million years of the Earth's history. That's what used to be referred to as the Hadean era. And now that this paper is published, they're saying maybe we need to refer to it as the Cryogenian era. However, that name's already been taken. So they're going to have to call it something else, maybe the Cryo era. Cryogenian refers to the Sturtian glaciation, which happened just before the Avalon explosion, where you get the first animal life forms. It's a period of tens of millions of years where almost the entire planet was covered with ice. So that's what's referred to as the Cryogenian era, but this is an era that's much longer. Hundreds of millions of years where the Earth's surface is essentially frozen over. Now, how this was discovered was by developing a model for the formation of lunar tides. Now, before we get to the lunar tides, let me show you what we have on Earth. And so the moon is sufficiently close to the Earth that its gravitational pull on the near side of the Earth is stronger than it is on the far side. I'm supposed to point this way, yeah. Thank you, we're live streaming. So I'm supposed to point to this screen, not to that screen, but here in the class, you can look at both screens. Because as we see this diagram here, the gravity of the moon pulls stronger on the near side than the far side, which actually causes the oceans of the Earth to bulge up. And so, any of you who have been to the beach will recognize that you get tides. And it's a diurnal tide. Twice a day, you're going to get this high tide, and then you get a low tide when the Earth is away from direct contact with the moon. Now, you don't see this. Because the moon is only 1/80th the mass of the Earth, the tides on our planet are quite small. In fact, if you're in the Mediterranean Sea, it's almost impossible to measure. It's really a fraction of an inch. That's all. And that's true of big lakes. So if you're on Lake Superior gets tides, but they're very difficult to measure. They're fractions of an inch. Now, if you got wide open ocean, you can get tides of several feet. And if you go down to the beaches here in the LA area, that's what you're going to see, tides of a few feet. But there are places in the world where you've got these bays that basically funnel the tidal water, and you can get tides much bigger than just a few feet. Now, my mother's family grew up in Nova Scotia, grew up in a place called Spring Hill, Truro, which is not far away. And you go to Truro, you actually can watch the largest tides on the face of the earth. And so here's a slide of what they call the tidal bore. And so this is the rushing in of the tide in the Bay of Fundy between New Brunswick and Nova Scotia. And the tide comes in so fast that if you're on horseback, you cannot outrun it. It's literally moving at more than 30 miles an hour. And so, which has caused, any of you ever done anything that's what they call whitewater rafting? I've done that a couple of times. Here it shows tidal bore rafting, okay? Because it comes in so fast, it creates rapids, so they actually take tourists out to ride the tidal bore. And it's such that there's a river that flows out of New Brunswick. When the tide comes in, the waterfall actually gets reversed. So the water coming over the waterfall, the tide comes in so strong, the water goes over the waterfall. The river actually runs backwards twice a day because of the strength of the tide. Okay, the tide is 53 feet high. So this shows you low tide, and you see where those tourists are up there. The tidal waters will come right up to just underneath the concrete there at high tide. So they're there getting ready to watch the tide come in, and it's really amazing. The tide is low, then suddenly the bore comes in, and literally within a few minutes, the water pours up, literally 30, 40, 50, 53 feet high. It doesn't always come up that high because actually the tides on the earth are caused by a combination of the sun and the moon. But the moon's tidal forces on the earth are more than twice as strong as the sun's. But when the two of them line up, that's when you get an extra big tide. And that's when it can go not just 40 feet, but literally 53 feet. Okay, now, the earth being 80 times more massive than the moon, its tidal force on the moon is much stronger than it is on the earth. But the moon doesn't have water. And so, but what's interesting is we can actually see that the solid rock features of the moon have been bulged out because of the tidal forces of the earth. So yeah, when you actually look at the moon, it's not a perfect circle. It's actually slightly bulged out. You say by how much? Well, only by 2 kilometers. But when you compare 2 kilometers to 53 feet, and you think we're not just talking water, because you look at the earth, the solid part of the earth, it really isn't affected by the tides of the sun or the moon. It's there's just too much tensile strength in the rock. But the moon's gravitational difference on the near side of the moon compared to the far side of the moon is so strong, it actually bulges the moon outward. And so it kind of, if I were to exaggerate it, it would kind of look like this. Now, part of it is because of the rotation of the moon. And so the Earth, for example, is bulged out 8 miles at the equator relative to the pole. But it's not because of the tides of the Earth or the moon, it's because of the rapid rotation of the Earth that you get this slight flattening of the Earth's spherical shape. Now, with the moon only rotating once every 29 days, it doesn't make much difference. However, astronomers know that the moon was rotating more rapidly in the past, and it was Pierre Laplace. How many of you ever heard of Pierre Laplace? Okay, a few of you remember what you learned in high school. I'm very impressed. Okay, Pierre Laplace was kind of like the French Isaac Newton. Lived a little later than Isaac Newton, but he was the most famous French physicist of that era. And interestingly, I found this out. You can go online and you can read the set of books that the King of France commissioned him to write, which is basically the very latest on the dynamics of the solar system. And one whole volume, volume 2, was devoted to studying what he called the rotational tidal bulge of the moon. And what Pierre Laplace determined more than 200 years ago is that the tidal bulge, so if I were to go back here, you can see that the moon is slightly bulged out a little bit. You can't tell because, I mean, after all, it's what, 3,500 kilometers across. You only got a 2-kilometer difference. But astronomers back in the days of Laplace were able to measure that with some precision. Then Laplace worked out the mathematics of the tidal forces of the Earth and the rotation of the moon being just 29 days, and he determined that the bulge was 20 times too big. In other words, the current tidal force that the Earth exerts on the moon is not strong enough to produce the bulge that we see. And it was Laplace that proposed an answer to this. He says, well, if the moon were closer to the Earth in the past, and if it were rotating more rapidly in the past than it is today, and given that we're looking at solid rock, maybe what happened is that the moon, when it was forming, would have been softer than it is today. And with the moon rotating more rapidly, the moon closer to the Earth where you get a stronger tidal pull. And keep in mind, the tidal force is proportional, inversely proportional to the distance between the Earth and the moon to the third power. In other words, if you were to move the moon half as close to the Earth as it is today, the tidal force would be 8 times bigger, 2 times 2 times 2 bigger. And so he says, if we have the moon much closer to the Earth, rotating more rapidly, and for some, the moon was softer back then, what would happen is the bulge fossilized. I mean, so kind of like what happens with fossils here. They turn to rock, and when they turn to rock, they're rigid. And so basically they said what we see on the moon is a fossilized bulge. It formed long ago, and it got frozen in place because we're talking solid rock. It's not soft anymore. And so we're actually seeing is the bulge that the moon had billions of years ago. Yes?
So the Earth and the moon both did have times when they were molten, or no? They no longer take.
Well, when the planets were forming, yeah, they were more molten. Or what Laplace was saying, we don't have to have them completely molten. We just have to have them kind of like putty, soft. That's enough for the tidal forces to bulge things out. And that soft stuff or molten stuff, either way, whether it's molten or simply just, like plasticine, the tidal force, and that turns to solid rock and crystallizes permanently, you can fossilize the original bulge. So yeah, the bulge today is 20 times too big, and it says, therefore, what we're seeing is a fossil bulge. Now, that's been around, yes, go ahead.
Just a quick follow-up question. Does the moon have similar concentrations of uranium and thorium like Earth does?
The Earth has way more uranium and thorium than the moon has. In fact, the moon forming event is part of the reason why Earth has so much uranium and thorium. And so, yes, because we're so richly endowed in uranium, thorium, we have plate tectonics. The moon does not. Yeah. So, and just to clarify, our body, planet Earth, compared to other rocky bodies of the same size, has 630 times as much thorium and 340 times as much uranium. So if you didn't know that, we're sitting on the uranium-thorium champion of the universe. And it's because of that you can all be here in class. If it wasn't for that, there'd be no possibility for human life. I'm not going into the technical details. If you're interested, it's covered in both Why the Universe is the Way It Is and the 4th edition of The Crater and the Cosmos. Yes, John?
Well, I had heard that there is a land tide, that we go up and down 6 inches every day.
Okay, there is a land tide, but it's not what we see here on the planet Earth. Yeah, the most visible part of the tide, there actually is a tide in the atmosphere too. But the easiest way to see the tide is going down to the beach and see what happens in the ocean. Okay, yeah, where was I? Yes.
Would that tidal force act on the fault lines? And could it trigger an earthquake? What?
Yes, tides do exert a force that could play a role in igniting an earthquake. We think there may be other ways. It means all kinds of ways you can ignite an earthquake. People are worried that the nuclear testing going on in North Korea could generate some earthquakes. There's also concern that if we build dams and store up a lot of water, the weight of the water could disturb an earthquake fault. All kinds of things can disturb an earthquake fault.
How about fracking?
Fracking could do it too. I mean, if you want to panic, there's all kinds of things that can. But you know, even without fracking, even without tides, even without that dictator in North Korea, or building dams and storing water, you're going to get earthquakes. So, uranium and thorium will generate earthquakes. But without earthquakes, you won't have continental building. Without continental building, you can't recycle nutrients. If you can't do that, you can't have plants and animals on planet Earth. So, thank God for earthquakes. Thank God for all the uranium and thorium. And hey, if you're living here in California, you're consuming more uranium than, somebody's here from Colorado. Yeah, you'll also get an extra dose of uranium in Colorado, but I hear that California, there's more uranium in our vegetables than there is in other parts of the world. And therefore, your life expectancy is reduced by about 1 month if you're eating foods from California. But last time I checked, most of the nation is eating vegetables from California, so I don't think it really makes much difference where you live. And for those folks living in Colorado, if you're living in the Denver area, your life expectancy is reduced by 3 months. So in that case, but I think there are other factors that are more significant in how long you live. So, and no matter where you live, there are natural factors that are reducing your lifespan. Actually cover that in Navigating Genesis. There was a time when people could live 800 or 900 years. But we got environmental factors now that make that impossible. Okay, getting back to where I was. What these 3 scientists did in their paper in Geophysical Research Letters, they went beyond what Pierre Laplace had done. And incidentally, many scientists have been studying this fossil bulge. But these 3 were the first to come up with a dynamically consistent computer model for the formation of the bulge on the moon. And what they concluded in their model is that previous models were making the point that the fossilization happened within just a few million years or less. And this being the first complete dynamically consistent model, they said, we now know that that's incorrect. That instead of taking just a few million years, it took a minimum of 300 million years and probably more like 400 million years for the fossilization to be complete. What they basically looked at, and incidentally, they had data that Pierre Laplace did not have. They had data. How many of you have ever run into people who claim that the lunar landings by the Apollo program were a fake? Okay.
I've heard that.
Okay, you've heard that? One thing you can tell people is this. I think it was the first men that went to the moon that put a laser reflector on the moon. Was that the first mission or the second mission? I think it was the first. It was the first. Okay, that laser reflector is used literally every day. Now say, why they put that laser reflector on the moon? They wanted to test theories of general relativity. You know, back in the 1970s, we didn't have really definitive tests of the reliability of the theory of general relativity. And so what they did is they put this laser reflector on the moon, and lasers here on the Earth would bounce laser light off that reflector and then time how long it takes to get back to the Earth. And literally, that's been used every day since 1969. And that laser reflector is still there. If anybody says nobody's been to the moon, well, somebody put that laser reflector there. So, because you couldn't do these kinds of experiments unless there was a very finely engineered laser reflector up there. But they had a byproduct from that experiment. They not only were able to come up with a more definitive verification of the theory of general relativity, they were able to determine that the moon is actually moving away from the Earth at about 3.9 centimeters per year. So there's a reason why Laplace couldn't measure it. It was very tiny. But with his laser reflector, they could measure that indeed the moon is slowly spiraling away from the Earth. Now, that means that the moon had to be much closer to the Earth in the past. And now that they've studied this for literally 4 decades, these 3 geophysicists were able to use data from these lunar reflector measurements to come up with much better estimates of where the moon was in the past, not only where the moon was in the past, but how rapidly it was rotating in the past. So yeah, they have data that Laplace did not have. And basically they're able to determine at the time of the origin of life on planet Earth, the moon was 128,000 miles away, which is almost half of a distance. It is 238,000 is where it is today on the average. So 128,000. And then they were able to project it before that as well. And so this is where they were able to determine, okay, looking at the lithosphere of the moon, which is kind of the crust of the moon, knowing how close it was to the Earth, and they were able to determine how fast it was rotating back then. But the bottom line was, they said, the fossilization took place over a long period of time. However, this would have consequences for planet Earth. If it did take 300 to 400 million years to fossilize, that would mean that the dissipation of the tidal interaction between the moon and the Earth was quite low in order for it to take that long. And what they concluded was, if there was liquid water on the Earth, then the dissipation wouldn't be as low as it is. But if we're talking the water being completely frozen, then it's consistent with the dissipation being low enough that it could take more than 300 million years for the fossilization of the moon's bulge to take place. So now, let me pull this in here, sorry. This shows you the brightness of the sun with respect to time. Basically making the point that when the sun first formed, it was accumulating mass and rapidly brightened. The brightness of a star goes up with a 4th power of its mass, so it dramatically brightens, then it loses mass and dramatically dims, and then it stops losing mass, stops gaining mass, and it ignites nuclear fusion. And when you ignite that spark, where hydrogen is now being fused into helium, the sun gets brighter and brighter in a very predictable rate. And this shows you the brightening, basically making the point that at the time that these moon's bulge was being fossilized, the sun was only 70% as bright as it is today. And basically what they're pointing out is, if the bombardment rate of planet Earth is much lower than what we presumed, given how dim the sun was back then, indeed Earth's water would be frozen. And that would explain the very low dissipation we see that's implied by the bulge of the moon taking hundreds of millions of years to fossilize. So he says, we need to rename the Hadean era. It's not hellishly hot, it's frozen cold. Now, there's a problem. They have found zircons that show that there were times between 4 and 4.4 billion years ago where the Earth had liquid water. And there have been several papers published about this over the past 7 or 8 years. However, these researchers didn't put this in the paper, but here's something that I can show you to explain it, is that we have much less bombardment than what we thought in the past, but there's still bombardment going on, bombardment where if you get a big comet or asteroid hitting part of the Earth, it's going to heat up that part. I mean, you know, it's the kinetic energy. I mean, these things come in at about 100 kilometers per second, and the energy that's released when it hits the Earth goes up with the square of the collision velocity. So at 100 kilometers per second, you're going to get enormous amounts of heat. I don't know, how many of you ever seen that meteor crater out in Arizona by Winslow? Okay, a lot of you have seen that. If you haven't, it's a spectacular place to go. Shows you a crater nearly a mile in diameter, about 350 feet deep, caused by a 100-foot diameter rock. A rock that tiny blew out a hole, and they calculate the heat release when that 100-foot rock hit there in Arizona, as was equivalent to the atomic bomb that wiped out Hiroshima in 1945. It generated as much heat as that nuclear explosion and caused a crater of about the same depth. So,
What year did that happen?
about 10,000 years ago.
Oh,
And you say, when's the next one going to happen? Well, they happen roughly every 10,000 years. So, but it's random, and it's not going to happen tomorrow. So,
They do like Siberia.
yes.
Since the moon is at a convenient distance now compared to what it was, what kind of useful data do we get out of these eclipses every once in a while?
What kind of data do we get out of the
What kind of
eclipse?
useful data?
Sorry.
Other than going, hey, wow, look at that. Yeah.
Sorry about that. I should have turned off my mic.
Aaron Page.
Okay. Several of us in the class actually went to see the solar eclipse up in Oregon back in August. And we actually had a few lectures on some of the unique things we learned from these eclipses. It was lunar eclipses, and most of us have seen a lunar eclipse. There's about 2 per year, and you can see them over half the planet. There was one just a few weeks ago. Yeah, that we were able to see here, a total lunar eclipse. Greek astronomers, Greek and Egyptian astronomers 2,500 years ago were actually able to look at lunar eclipses, and they were able to determine that the eclipse was caused by the shadow of the Earth, and they saw that it was curved, so it led them to conclude that the Earth must be a sphere. And they're able to use the size of the curvature to determine the relative size of the Earth and the Moon, and even determine through solar eclipses how far away the sun was. Now, it wasn't accurate. They were off by a few times, but it was sufficient for them to determine the sun was much, much bigger than the Earth was bigger than the Moon, and they had a rough idea of the relative distances, and that led them to conclude that we live in a heliocentric system, where the planets orbit around the Moon. And you say, well, how come came up with this idea that the Earth was the center? Well, it was a Greek astronomer told me, and keep in mind, back then, astronomers earned a lot of their money from people who were interested in astrological forecasts. And so incidentally, the Christian astronomer Kepler, he actually got his financial support from people who wanted astrological forecasts. He wasn't involved in that at all. But astrology critically depends on coming up with the future positions of the planets in the sky. And so it was really important to support the funding of astronomical research, that these astronomers be able to predict with some precision the future positions of the planets in the sky. And Ptolemy said, well, we can't do that if we put the sun at the center of the solar system. Our math simply won't give us the answers we need. But if we just assume that the Earth is the center, we can use the plane geometry that the Greeks gave us, and it will show us through an epicircle approximation where the future positions of the planets are. It's actually quite accurate. And that kept the astrologers happy, and they kept giving money to the astronomers to do the research. Today we get our funding from other sources, and so we're not dependent.
So basically, it's just, hey, isn't that cool? That's just-
Yeah, but here's the point. A lot of people think that Christians thought that the Earth was the center of the solar system, and that scientists back then concluded the Earth was the center of the solar system. The real truth of the matter is they didn't have algebra. If you don't have algebra, you cannot determine with precision the positions, future positions of the planets. But with plane geometry, you can, but you have to assume the Earth is at the center. And so Ptolemy actually knew the sun was the center of the solar system. He says, here's a mathematical tool that will keep money coming in to support our astronomical research. Yes,
So, the Hadean.
I'm off subject. We're going to close this up and get back to it. Go ahead.
So the Hadean era, which formerly was about 4.4 billion down to 3.85 billion, right in that range. Is any of it surviving this new theory, or is it totally gone? No molten surface, always frozen? Or a combination?
Okay. The status is, this is the first research group to determine that the bulge of the moon took hundreds of millions of years. And this is quite different from what people thought. I mean, this has been in textbooks literally for decades. This, what you see here is the bombardment history of the Earth from the time it formed till about 3 billion years ago. And from that point forward, it's a pretty flat curve. And it shows this called the late heavy bombardment at 3.9 million years, 3.9 billion years ago. That's another piece of evidence you can give to people who say, we didn't go to the moon. It was rocks that were brought back from the moon, which basically persuaded scientists there had to be this late heavy bombardment because of the dates they were getting on the formation of those rocks, which caused them to look more carefully at the cratering on the moon. And so with high resolution telescopes, they were able to look at the moon's craters. Let me bring back the image of the moon here for you. Okay, if you actually look with a big telescope at the craters, you can see that those craters are slightly weathered. You say, what's weathering those craters? Well, you probably have been taught that the moon doesn't have an atmosphere. It actually has a very, very tiny atmosphere of argon. Say, where did the argon come from? The decay of potassium. And so potassium in your body is decaying into argon. So you're literally radiating argon gas. Not very much. So, and yeah, it doesn't smell. It's an inert gas, so don't worry. No jokes, okay. But because of potassium decay, even though the moon has no other gases, it's got argon. And its gravity is strong enough, because argon's a heavy gas, it's strong enough that the argon doesn't escape to outer space. And so even with its very slow rotation and that tiny amount of argon gas, it's enough to slightly erode the craters. But it erodes the craters very, very slowly. But as we look at the erosion of the craters of the moon, we see that more than 90% of them show an erosion history that's consistent with those craters forming about 3.9 billion years ago. Incidentally, we see the same thing on Mercury, and to a lesser degree on Mars, because Mars has quite a bit of erosion, but it's consistent. So the 3 planets we're able to look at long-term crater erosion are consistent with the whole solar system being heavily bombarded. Let me pull this back up. Sorry about the animation. Here we go. It's consistent with the whole solar system receiving a very intense bombardment 3.9 billion years ago. And so the textbooks have been saying, well, in the early solar system, we still have lots of debris, so the bombardment goes down exponentially. You get the late heavy bombardment, then it declines and basically dissipates down to a virtual zero where it is today, with the exception of things like you see in Arizona and in Russia. Okay, and possibly even here if we're unlucky, yes.
Well, the tidal coupling that increases the energy of the moon's orbit and causes it to recede also causes the Earth's rotation to slow, so our days are getting longer because of that.
They are. Not by much, but every year we have to correct by a few microseconds. And that's all caused by the tides of the sun and the earth. So yeah, our rotation rate is getting slower. And incidentally, a time will come because of the tidal interaction when we will be having a rotation period that's the same as the moon. So just like we have one face of the moon tidally locked to us, a time will come when one side of the earth will be tidally locked to the moon. And our rotation period then won't be 24 hours a day. It's going to be 40 times as long. Okay. When will that happen? Well, it's going to take about 40 billion years. Yes, go ahead.
Was it frozen during the 3.9?
Pardon me?
That was part of my question.
What?
At 3.9, late heavy bombardment,
Yes.
was the Earth still frozen during that time?
Okay, the late heavy bombardment is so intense and so spiked that you see there, it's going to be hot. And that also explains why you don't really see permanent rocks until after the late heavy bombardment. Because you know, the Earth has to cool enough from the late heavy bombardment that you can have rocks that remain as rocks. Okay, and
And that
yeah,
was sort of my question.
Yeah.
Yes, I'm assuming that the Earth is still very viscous at this time. By the way, I want to make a comment for today, separate from that.
okay,
On the time change and the upsurge of flat Earth paranoia, or whatever you want to call it. I don't know if that comes from Trump's fake news or what, and everybody's thinking it's fake news. But on a time change, if the Earth were flat, there would be no need for time changes because the angle of the sun to the Earth would be the same in all places. But the fact that we have a time change, we need to think that there are different angles coming in. And of course, eons ago, centuries ago, who would know or who would care if you're on horseback or foot? You don't even notice the time change. But with trains in the 1800s, and especially now for flat Earth, how do they answer that? So anyway, back to the question. You sort of answered it, but was the Earth really viscous and formable and maybe solidified to a bulge after the 3.9?
okay. The Earth also has kind of a fossilized bulge. And so, yeah, I mean, but in the case of the Earth, the rotation of the Earth is a much bigger factor than the tides. In the case of the moon, rotation is a factor, but the tides are also a big factor. So it's both the tides and that's why they call it the tidal rotational fossil bulge. But in the case of the Earth, you can almost ignore the tidal effect. As you pointed out, in terms of the solid rock, it amounts to a couple of inches, that's it. The rotation is the big factor for why it's bulged out by 8 miles. Yes?
Not to keep staying off the subject, but how about late heavy bombardment and plate tectonics? You want to say something?
The late heavy bombardment would have affected plate tectonics.
Drastically?
Yeah, drastically. I mean, they're talking within a 100 million year window, 30,000 plus big bombardment events of the Earth. And by big bombardment events, they mean boulders the size of a kilometer in diameter or more. So yeah, that will make things hellishly hot in the face of the Earth. So maybe one way we can save the term Hadean era, you can refer to it as the spike era. That's when it would have been hellishly hot for that period. If you want to read the latest on that, I have it in Improbable Planet. There's actually a couple of other theories that are being debated here. But to answer your question, is this now textbook stuff? When you publish a paper like this, it's different from what anybody else said. It doesn't get into the textbooks. It takes confirmation. In fact, the 3 authors made the point. We're going to continue studying this. This is basically their first paper on this, and they said, we can get a lot more out of the data we now, because now we got quality data. And they said, this is our initial discovery. We're going to keep working on this, because one of the things they didn't do, well, what would be the effect on the Earth? And so they basically said, well, one fact we know is the dissipation is a lot less. We can't be talking liquid water over the whole face of the Earth. It's got to be in a frozen state. But they said, maybe we can learn a lot more about the early history of the Earth than we know now. We simply didn't go that far with our model. And of course, other teams are going to need to jump in, and other disciplines are going to have to jump in. And so it doesn't really become textbook stuff until you got multiple scientists working with different independent experiments, basically coming up with the same answer. But I call this a breakthrough because as I read the paper, I think they got the goods. They really are demonstrating that most of it is frozen. But one thing I want to mention, how do you explain the zircons? Because that was one of the critics of this paper said, we got the zircon evidence that tells us that it wasn't frozen, it was liquid. Now, the zircons they're talking about are really tiny crystals. I mean, you kind of can hold them like this. We're talking like a millimeter. And we only have a few zircons between 4 billion years ago and 4.4 billion years ago that show evidence of liquid water. In fact, I mentioned, I got an article, a blog coming out on this tomorrow. Make the point, since we only have a few of these zircons, that would be consistent with us having between 4 billion years ago and 4.4 billion years ago, isolated sites on the Earth where there's been a bombardment event that turned the frozen surface of the Earth in that locale briefly into a liquid state. I think that would be consistent with the fact we've only found a few zircons in a few locations that show this evidence of liquid water. And yeah, if something like what created that crater in Arizona were to happen in this era here, then where it hits, the frozen water will briefly become liquid. So I think it's consistent with the zircon evidence, and therefore what the paper is concluding is the bombardment history of the Earth must look more like this. Not this, but this, where we have this period of 300 to 400 million years where the bombardment is so low that the Earth's surface predominantly is in a frozen state. Yes, and then I'll get back to you.
I got a couple questions. First of all, is that you see lots of curves like this of the intensity of solar radiation. What we don't see is a plot of the expected Earth's surface temperature during this time. For example, if you have ice at the beginning, okay, that's going to be a low temperature, and then you hit it with a bombardment that's going to increase it. So, do people estimate that? That's one question. The other question is, you talked about a lot of concern about the rotation rate of the moon. And we know the moon the moon is tidally locked, so that it's facing us, gives us the constant face at all times. So if that's the case, the rotation rate of the moon is then tied to its revolution rate around the Earth. So that would seem to be, I mean, if it really is strictly tidally locked, we would know its rotation rate from that rate of revolution. But those are my two questions. What's the discrepancy?
Okay. Tidal physics is pretty easy to work out, as Laplace showed us more than 200 years ago, if the distances between the two bodies is sufficient. The problem is this data tells us that the moon was closer than that, which means that the tidal physics is much more complicated. Sufficiently complicated, you need to know exactly what the constituents of the moon and the Earth are, their temperature, their rotation rates, and and this has been in the literature for the past several years, that what we teach students in undergraduate level about tidal forces, all that goes out the window if the bodies are close together. Now we're looking at really messy mathematics. And they admitted that in the paper. They said, we're working on it. And so they basically were looking only at the impact on the moon predominantly, and then what the dissipation forces on the Earth. They said, we're going to go back to the drawing board, because they said, we got good data. We're going to be able to come up with a more definitive model. This is typical, by the way, in physics and astronomy. In order to establish kind of your pecking order, you publish initial results. You don't wait till you got the whole story. You publish your initial results, which kind of gives you some priority in the publishing. and then you publish 2, 3, 4 papers. I expect this is going to be a set of at least 4 papers where we say, here's the later stuff that we've learned. So the answer to your questions, hopefully they're coming. But right now, it's a big unknown. Because as you point out, yeah, you got to know a lot more about the viscosity of the Earth, the temperature of the Earth, what was going on in the interior of the Earth, the energy flow from the interior to the surface. You got to know that for the moon as well. And, you know, it might not have always been tidally locked. When did tidal locking occur? And there's been models pointing out you can get, because I mean, when you've got the bodies close together, the force that generates tidal locking is very strong, but there are ways it can be broken. And so they think that, you know, the best models tell us that there were episodes of tidal locking and breaking from tidal locking. Now, again, this is all up for grabs and for greater discussion.
How about the temperature of the surface of the Earth versus time?
Well, yeah, the bombardment's going to change the temperature of the Earth. What these people were pointing out is, you know, when we kind of looked at this, they said we didn't really take into account adequately what was going on with the physics of the sun. And so realizing that the sun was a good 70% dimmer 4.2 billion years ago, then this really points to more of a bombardment history. It looks like this. Because if the sun is not putting as much heat in the surface of the Earth, then even if you're getting bombardments, it's still going to be cold. However, even taking that into account, this paper is basically telling us it was not as bombarded as heavily as what we think. It looks more like this rather than like that. Whoops, wrong way, sorry. I lost the computer. Wait, what happened here? Okay, it's going to have to come back up. Anyway.
A little bit of a Ken Griffin pinch.
But this,
There it is. Okay.
this doesn't describe the temperature of the surface of the Earth.
No, this
That-
simply,
which is what I was asking about.
yeah. Well, the temperature of the Earth, bottom
Of the
line,
surface.
is cold enough that you get ice.
Okay, so you start out cold and you go through a hump with a later bombardment.
Well, the reason why they know it's ice is because of the low dissipation implied by the fossilization of the moon's tidal rotational bulge. Now, exactly how cold it is, the data doesn't tell us that, but cold enough that you're going to get permanent ice,
Yeah.
except for the local incidences where you get bombardment
Okay.
and it raises the temperature, which locally turns some of the ice into liquid water, which would explain why you got those zircons that show that. Something else that's not in the paper, which would tell me that even this needs to be revised, is the moon formation event. The moon formation event has now been dated pretty accurately to be about 95 million years after the Earth formed. And that's in the book Improbable Planet, why we have that good date. But for the moon formation models to work, the Earth at that time would have to have oceans of liquid water at least 1,000 miles deep. And they think 2,000 to 3,000 miles deep. And you know, that would be consistent with what we think Earth-like planets, that appropriate distance from the star, should have in the way of liquid water. In fact, that's actually a bit small for the liquid water, because Earth-like planets that we found where we can measure the quantity of water is between 5 and 50% water compared to the total mass of the planet. Now, the reason why we know the Earth at that time had to have these really deep liquid water oceans, the collision event that led to the formation of the moon wouldn't have just formed the moon, it would have destroyed the Earth if we're talking two bodies crashing into one another without the liquid water to soften the collision. And it's the turning of all the liquid water into steam that actually is a critical component in the moon formation event. What does that tell us? It tells us the bombardment would have to be sufficiently less intense, that the Earth, 95 million years after it formed, was having liquid water. It couldn't be steam. It had to be liquid. And so shortly after the moon formation event, it turns frozen. And so, yeah, you do have bombardment, but not sufficient bombardment to turn the water into steam, because if that was the case, the moon formation model simply fails. It does not work. And the moon's up there, so yeah, we know it formed. No doubt about that, it's sitting there. And so that tells us that even what they suggest in the paper probably needs to be revised, where we take the bombardment at a very low level all the way back to just, say, 60, 70, 80 million years after the Earth formed. So,
Could you reiterate on the dissipation, just to connect everything together again, how Earth and Moon?
okay. Well, basically, they determined in order that the fossilization of the moon's bulge was not a rapid event, like scientists have thought for the past 250 years. It had to be a very slow event. And they said at least 300 million years. And for it to be that slow, the dissipation of energy, tidal energy the moon exerts on the Earth, means that we're looking at the moon's tidal pull basically being exerted on solid features, not liquid features. And so rather than the water being liquid or completely gaseous, it would have to be largely frozen to explain the low dissipation that would be consistent with it taking hundreds of millions of years to form. The blog I'm putting out tomorrow actually explains this in layman's language. So, any other questions? Yes.
Hugh, I had a question. Your blog will probably explain this, but do you have a prediction yet of what how this will affect RTV's testable creation model, particularly the day 2 where God set up the hydrologic cycle? I mean, does this push it back? It seems like still the late heavy bombardment is still going to be pretty much the same sequence there. Is the earlier solid form of the Earth going to affect that?
Okay, the blog does not comment on creation day 2. This basically, either way it goes, it doesn't affect creation day 2. So that still stands. But it does have implications in 2 areas. First of all, this is not good news for young Earth creationists, because now we've got a detailed model that tells us here's an event that didn't happen in thousands of years, but hundreds of millions of years, and there's really no way out. I mean, you can't really explain the bulge of the moon in a young Earth model. But what's more important is the implication it has on the origin of life. Because if you've got because there's a lot of people speculating, well, this paper that says the origin of life happened very rapidly, 3.825 billion years ago, right after the late heavy bombardment, which means we're not looking at a naturalistic model. This is instantaneous. I mean, as soon as the temperature is appropriate for the origin of life, it's there immediately, and we're talking multiple species. Some people speculated, well, maybe the late heavy bombardment was episodic. The evidence says that it's not, but they've been speculating about this. I covered this in Improbable Planet, where they said maybe there were refuges deep below the surface of the bottom of the oceans, where life might have survived. In other words, yeah, there were bombardments, it was evaporating the oceans, it was liquefying the rocks, but it said if you got life deep below the bottom of the ocean floor, maybe it would have survived, and that life could evolve into the life we see at 3.825 billion years ago. I make the point in Improbable Planet, that simply won't work, because if you're actually going to spread out that late heavy bombardment, that means you've got temperature fluctuations, where it's going from high temperature to low temperature, and these life forms that exist below the bottom of the ocean floor, they're intolerant of temperature changes. So changing the temperature doesn't help you. Moreover, these are extremophiles. They have extremely low metabolism, and they simply do not have the capability of evolving into the mesospheric bacterial life species that the origin of life demonstrates. So they basically picked on the wrong species of life. And but you'll see the details in Improbable Planet, why I believe that model simply won't work, and actually makes the origin of life more challenging for the atheists rather than less challenging.
Now it's like Europa, they've got thousands of miles.
Well, if you've got frozen Earth, that's not a good model for any origin of life. You need warm temperatures. So this is why this is not good news. You say, well, what about those isolated places where we see the zircon evidence for liquid water? Well, what this would tell you is that's happening right next to a collision event. And a collision event, that's not good news for origin of life either. So it's basically telling us, this is giving us additional evidence that the origin of life can't possibly be a naturalistic event. We really do need an extraterrestrial being from beyond space and time that comes here and that creates the first life on planet Earth. So this is more evidence, and that to me is the most important part of this discovery. But in response to what you're saying, this is just the start.
You know, you say that.
No more questions or comments. It's time to end. Hugh, we do have one online question that you can answer with a yes or no. In this late heaven bombardment, did all the water on planet Earth turn to steam at some point, yes or no?
Did all the water on planet Earth turn to steam? Well, I can't really answer that as yes or no.
I mean, it was pretty hot. It's hot enough that's a possibility. No, okay, but then it's a possibility it could or could not. Then.
Okay. Given the fact that we see oldest rocks at about 3.83 billion years ago, and that tells us that the Earth had to be in a very hot state to explain why we don't see permanent rocks until that time. That's consistent with the late heavy bombardment. We've got good evidence from the dynamics of the solar system that the late heavy bombardment is real. So yeah, the answer fundamentally is, I forget what, yes or no.
Yeah.
You got to ask the question
yes,
again.
Did all the water on planet Earth turn to steam at one point in time?
Well, all the water did turn to steam briefly. However, I do point out an improbable planet. It depends how the late heavy bombardment hit. I mean, if all the bombardment were to take place in Siberia and nowhere else, that would raise the temperature of the Earth through volcanoes to turn everything into steam, even though you don't have evenly distributed bombardment. So yeah, the answer basically is the water would be steam, the rocks would be molten, and you got to wait a few million years, tens of millions of years after the peak of the late heavy bombardment before you can have stable liquid water and stable rocks. But before the late heavy bombardment, even with the Earth predominantly frozen, you will get places where very briefly you get rocks, well not rocks, you get crystals, and you get liquid water. So hopefully that answers it.
Close and prayer now.
Oh, yeah, we need to get a clock here so I can tell what's going on.
I know, time flies in this room.
Time flies. Yeah, I saw it fly a little while ago, so. Hopefully a clock will fly up there on the wall. But yeah, I mean, I appreciate a clock because my intent was we would get a start on the Isaiah passage. What we're going to do next week, no scientific discoveries, even though another big one happened this week. You're going to get my blog article to see it. We're going to spend the entire time on the book of Isaiah. And thank you for collecting all these passages relative to what Isaiah's got to say about the beginning of the universe. I've actually got slides in all this. We're going to go through all the verses that you collected rapidly, get the general sense of what it's saying, and we're going to go after each verse one at a time. And you'll be amazed at how much detail the book of Isaiah gives us on the origin of the universe and God's role in all that. With that, let me pray. Father in heaven, I want to thank you, Lord, for the privilege that all of us here are living in the 21st century. A time when your prophet Daniel said, explosion, knowledge is exploding. And indeed, Lord, what we're learning about the realm of nature literally is exploding before our eyes to such a degree that the internet is just saturated with all these discoveries. And thank you, Lord, that we live in a day and an age of technology when we can actually access all this stuff without having to pay big subscription fees or being a PhD scientist. It's available to all of us. And Father, you commanded us to study the book of nature as well as the book of Scripture. Thank you for giving us such great access to both books. Help us in our study of it to see your handiwork and your glory and to communicate to others how that glory reveals your righteousness and your plan of salvation. In Jesus' name, amen.
Amen.
Thank you.
If you came to class late,